Welcome to AI Paper Podcasts, where we unpack the freshest research in artificial intelligence. Today, we're diving deep into a crucial challenge for long-context large language models, the ever-exploding memory demands of their key value caches. We've got a fascinating paper you shared, XKV Cross-Layer SVD for KV cache compression, which offers a really clever and surprisingly effective solution.
That's right. For those pushing the limits of context windows, now reaching into the millions of tokens, the KV cache has become a major bottleneck. This paper tackles this head-on with XKV, which is a post-training method. It uses cross-layer Singular Value Decomposition to compress the KV cache.
Okay.
The core idea, instead of focusing on token-level similarities, XKV finds shared patterns, these aligned dominant singular vectors across different layers.
Okay, let's unpack this fast for our short-form viewers first.
Yeah.
The KV cache in long-context LLMs eats up memory big time. XKV, a new post-training compression method, addresses this by applying Singular Value Decomposition, SVD, across groups of layers. This finds shared patterns, compressing the cache into a shared low-rank space. Think of it. Consolidating information instead of storing it, redundantly. Evaluations on models like Llama 3.1 and Qwen 2.5 show XKV achieving up to 6.8x higher compression and, get this, 2.7% better accuracy than previous interlayer methods.
Yeah, that accuracy boost is pretty striking.
It even works with multi-head latent attention models like DeepSeek Coder v2, getting 3x compression on coding tasks without losing performance. The key insight, the main themes of information storage, those dominant singular vectors, are surprisingly aligned across layers, even if the fine details of individual tokens aren't. So XKV leverages this shared structural backbone for really efficient compression.
And for our regular viewers diving deep with us, our mission today is to fully explore XKV. The problem it's solving, the smart thinking behind it, the technical details of how it works its magic, and the really impressive results it delivers on cutting-edge models. We want you to understand not just what XKV does, but crucially, why this approach is so effective and what it means for the future of deploying these massive language models.
So let's get right to the heart of it. Why is this KV cache such a pain point in the first place, especially as context windows get longer and longer?
Well, it's fundamentally about memory efficiency. To process a sequence of tokens, LLMs store the key and value states for each token in their context window.
Right, the attention mechanism needs that.
Exactly. This allows them to attend to any previous token without recomputing everything from scratch. But as you extend the context window to hundreds of thousands or even millions of tokens, well, the sheer size of this KV cache just explodes.
It's just enormous.
It is. And this has direct and significant consequences.
Yeah.
It limits the number of concurrent users a model can handle, and it drastically reduces the speed at which the model can generate output, the inference throughput.
Ah, okay.
In essence, it becomes a major roadblock for making these powerful models practically usable at scale.
It's like trying to download a massive file on a dial-up connection. You're just going to be stuck there for ages. Now, the paper points out that there have been previous attempts to tackle this, mostly focusing on shrinking the KV cache within each individual layer of the model, right?
Exactly. Techniques like quantization, which reduces the precision of the numbers stored in the cache.
Lowering bit count.
Right. Or token eviction, where you selectively discard less important parts of the context, operate primarily at the layer level. Similarly, when researchers have looked at low-rank decomposition methods, these have largely been applied independently to each layer's KV cache.
Yep.
While these intralayer methods provide some degree of compression, they inherently miss out on potential redundancies that might exist across the different layers of the neural network.
Right, like you're tidying up one room without checking if you have the same junk in another room.
Exactly. It's like tidying up each room in a house separately without realizing you have multiple copies of the same items in different rooms.
Which naturally leads us to the idea of interlayer compression. The paper mentions a couple of earlier attempts, cross-layer attention, CLA, and mini-cache. What were the fundamental limitations of these approaches that XKV aims to overcome?
That's a key point. CLA was an interesting concept trying to share a single KV cache across groups of layers. However, it required significant surgery on the transformer architecture itself.
Oof, major changes.
Yeah, and crucially, it necessitated expensive pre-training from scratch. That's a huge hurdle for adoption, especially if you want to apply these compression gains to already successful and widely deployed models.
Right, you can't just retrofit it easily.
No. Minicache, on the other hand, is a post-training method, which is a significant advantage. It attempts to merge the KV caches of adjacent layers based on the assumption that the token embeddings at each layer have a high degree of similarity measured by cosine similarity.
Okay, so it assumes the tokens look similar layer to layer.
It does. However, as the XKV authors clearly demonstrate, this assumption often doesn't hold true in practice.
So even if two adjacent layers are processing conceptually similar information as the input flows through the network, the way they represent that information at the level of individual token embeddings can be quite different.
Precisely. Think of it like different stages in a factory assembly line working on the same product. While the goal is the same, the specific tools and operations performed at each stage are distinct. Minicache's reliance on high token level similarity is like trying to directly merge the toolboxes of two different stages. Just because they're both working on the same product, it likely won't work very well.
I see. So that mismatch is why it doesn't perform as well.
Yeah, this mismatch often leads to significant drops in the model's accuracy when compressed with Minicache, as the experimental results in the XKV paper clearly illustrate.
Okay, so that paints a clear picture of the challenges. Now, what's the central, perhaps even surprising insight that the authors of XKV uncovered that allowed them to take a more effective path?
Here's where it gets really interesting. Instead of focusing on that granular per-token cosine similarity, the XKV team decided to re-examine interlayer similarity using a different lens. Centered kernel alignment, or CKA.
CKA, okay.
What their analysis revealed was quite remarkable and perhaps counterintuitive. They found that even in scenarios where the token level similarity between layers was low, the dominant singular vectors of the KV cache across multiple adjacent layers were often surprisingly well aligned.
Wow.
This is the core discovery that XKV leverages.
Dominant singular vectors. Okay, for our audience of AI researchers and ML engineers, this will resonate, but let's just offer a more intuitive way to think about this for anyone who might be less familiar with the intricacies of linear algebra. How can we understand the significance of these dominant singular vectors in the context of the KV cache?
Right. Imagine the KV cache as a complex, high-dimensional space representing how information is encoded for each token within a given layer. Singular Value Decomposition, or SVD, is a mathematical technique that helps us decompose this complex space into its fundamental components, or like directions of greatest variance.
The main patterns.
Exactly. The singular vectors are these principal axes, and the dominant singular vectors are simply those that capture the most significant amount of information, the most prominent patterns, and how the data is structured within that layer.
Okay.
What the XKV authors discovered is that these core patterns, these fundamental ways the information is being organized across different layers, tend to be very similar, even if the fine-grained details, the exact numerical values in the token embeddings are not.
Huh. It's like recognizing the same underlying melody played with different instruments. The notes might sound different, but the core structure remains.
That's a really good analogy, precisely. This alignment of these dominant underlying themes is the key that XKV cleverly exploits. It suggests that we don't need to store completely separate, fully detailed representations of the KV cache for each layer.
Right.
Instead, we could potentially use a shared, more compact set of fundamental theme vectors to represent the KV cache of multiple layers much more efficiently.
Which brings us directly to the XKV method itself, cross-layer SVD. So how does this core insight about aligned singular vectors translate into a practical compression technique?
Building upon this crucial observation, XKV is designed as a post-training compression method. This is a significant practical advantage because it means you can apply it to already trained and high-performing models without the need for any expensive fine-tuning or modifications to the underlying network architecture.
That's huge for practicality.
It is. The central idea is to take a group of adjacent layers, for example, 2 or 4 consecutive layers, and horizontally concatenate their respective key and value caches. Then, the XKV method applies a singular value decomposition operation on this combined larger matrix.
Okay, so instead of doing SVD on each layer's KV cache individually, you're essentially treating the combined KV cache of a group of layers as one unified data structure for the purpose of finding these shared patterns.
Exactly. By performing SVD across these concatenated layers, XKV effectively identifies the shared principal components, or dominant singular vectors, that best capture the essential information across the entire group of layers. It then represents the KV cache of these grouped layers in a shared lower dimensional subspace.
Got it.
Instead of each layer having its own full-rank KV cache, they now share a common lower dimensional basis, along with layer-specific reconstruction matrices that allow each layer to reconstruct its original KV cache from this more compact shared representation.
So it's like having a shared library of fundamental information building blocks, and each layer just needs to store a much smaller set of instructions on how to assemble these building blocks to represent its own KV cache.
That's an excellent way to think about it. The shared basis, the common singular vectors, acts as this library of fundamental building blocks of information patterns, and the layer-specific matrices act as the assembly instructions, telling each layer how to combine these shared patterns to accurately represent its own key and value caches. This sharing of the underlying basis is where the significant reduction in memory footprint comes from.
Let's dive a little deeper into the technical implementation. The paper uses notation like XGIL to represent the key or value cache of layer $. Can you walk us through the cross-layer SVD process with a bit more of that technical detail?
Certainly. For a designated group of layers dollars with indices ranging from $to $, their key or value caches are first stacked horizontally. So if we're looking at the key cache, we'd have a combined matrix XDHL key go bring bufun.
Just sticking them side by side.
Yep. This resulting matrix has dimensions of sequence length $ by D, where D is the hidden dimension of each layer. Then singular value decomposition is applied to this combined matrix, GSRAT, the standard SVD components.
Right. Here, GT is an all-talar matrix containing the top talar singular vectors. This is our shared token basis.
Yep.
ZTOR is an all-lar talar diagonal matrix containing the top talar singular values, which represent the importance of each singular vector. And VATOR is an all-talar DJOLT matrix containing the right singular vectors. This decomposition can be reformulated as DAT, where SEINAD is the shared token basis of dimension $ times oral, and each baller is a layer-specific reconstruction matrix of dimension times DD. The key here is that $, the rank of the approximation, is significantly smaller than the original combined dimension, leading to compression.
And how do they decide which specific layers to group together for this cross-layer SVD? Is there a sophisticated method for determining these groups? Actually, the paper adopts a surprisingly simple yet effective strategy called stride-based grouping. They divide the sequence of transformer blocks into contiguous non-overlapping groups of a fixed size D dollars, such as groups of 2 or 4 adjacent layers.
Just simple blocks.
Yeah, simple blocks. The rationale behind this straightforward approach is directly supported by their earlier observation of strong singular vector alignment, primarily between layers that are close to each other in the network, as evidenced by their centered kernel alignment analysis. Figure 2b in the paper visually demonstrates this pattern of high CKA scores between adjacent layers.
That makes intuitive sense. You'd naturally expect layers that are closer in the processing pipeline to be dealing with more similar representations of the information. Now, what about the practical application of XKV during the inference process? How does it integrate into the prefill stage, where the initial prompt is processed, and the subsequent decode stage, where new tokens are generated?
Right, so during the initial processing of the input prompt, the prefill phase, XKV operates by first gathering the key and value states for each predefined group of layers. It then performs the cross-layer singular value decomposition on these concatenated caches on the fly.
On the fly. Okay, so it's dynamic.
It's dynamic input-dependent decomposition. This allows XKV to capture the specific characteristics of the KV cache for the given prompt. Interestingly, the paper reports that the computational overhead associated with this online SVD during prefill is quite manageable, measured at less than 10% for a context length of 128,000 tokens and becoming negligible for even longer contexts.
Wow, that's not bad at all.
Not bad. Furthermore, the authors suggest that this technique could also be applied to prefix caches to reduce both storage and communication costs in certain scenarios.
That on-the-fly decomposition during the initial prompt processing seems crucial for adapting to different inputs. What then happens during the token generation, the decode phase, where the model is actually producing new parts of the sequence?
For the generation of new tokens, the KV cache generated for these new tokens is typically not compressed initially.
Ah, okay.
This is because in typical long context applications, the size of the KV cache accumulated during the relatively short generation phase is considerably smaller than the KV cache generated from the much longer initial prompt.
Right, the prompt cache dominates.
It does. Therefore, leaving the KV cache for newly generated tokens uncompressed introduces a negligible memory overhead while helping to maintain generation quality, a finding consistent with other KV cache compression research. However, in use cases involving exceptionally long generations, XKV could be reapplied to the accumulated generated tokens as needed.
Makes sense.
During the decoding steps, when the model needs to access the compressed KV cache from the initial prompt, it simply reconstructs the approximate KV cache for each layer by multiplying the share basis matrix Elitaler with the corresponding layer-specific reconstruction matrix Elitaler.
Okay, that clarifies the mechanics of SKV throughout the inference pipeline. Now let's talk about the results. The paper presents some really compelling empirical findings across a range of state-of-the-art models and challenging benchmarks. What were the key highlights that stood out?
The experimental results are indeed very encouraging. The authors rigorously evaluated XKV on the demanding ruler benchmark, which is specifically designed to test long context understanding capabilities. They used highly competitive models like Llama 3.18b Instruct, Qwen 2.514b Instruct 1M, and Qwen 2.57b Instruct 1M for these evaluations.
Just serious models on tough tasks.
Absolutely. Furthermore, they tested the versatility of SKV on DeepSeek Coder v2 Lite Instruct, which employs the Multi-Head Latent Attention MLA mechanism, using the RepoBench-P and LCC benchmarks for code completion tasks. The performance of SKV was compared against a standard baseline with no compression, Minicache, the prior state-of-the-art in interlayer KV cache compression, and single SVD, where SVD is applied independently to each layer's KV cache. Importantly, single SVD also applied the decomposition on the fly during the prefill phase, providing a strong direct comparison.
Okay, so a fair comparison. And how did SKV perform?
Across the board, XKV demonstrated significant advantages in achieving higher compression rates while either maintaining or even improving upon the accuracy of the baseline models.
Improving accuracy, that's impressive.
It really is. On the ruler benchmark, Minicache exhibited substantial accuracy degradation, even at relatively modest compression rates, likely due to its underlying assumption of high token-wise similarity, which, as we discussed, doesn't always hold.
Right, that flawed assumption bites them.
Seems so. Single SVD performed reasonably well at moderate compression levels, but its accuracy dropped off considerably at higher compression rates. In stark contrast, XKV consistently achieved much higher compression rates, reaching up to 8.0x in some configurations while maintaining strong accuracy. In fact, on Llama 3.18b, XKV achieved up to a 2.7% improvement in accuracy over the best-performing baseline at comparable compression levels.
That's a pretty remarkable accuracy gain, especially at such high compression.
It is indeed, and a particularly interesting finding was that increasing the group size for the cross-layer SVD, for instance, comparing XKV with a group size of 2 layers, XKV2, to SKV with a group size of 4 layers, SKV4, often led to further improvements in accuracy at the same overall compression ratio.
So grouping more layers together helps.
It seems so. This observation strongly supports the idea that capturing a richer, more comprehensive shared subspace across a larger group of layers is beneficial for preserving the essential information. Even when applied to Qwen 2.57b1m, which already features a highly optimized and compact native KV cache, XKV still managed to demonstrate tangible benefits in terms of compression versus accuracy trade-offs.
And what were the results when XKV was applied to the DeepSeek Coder v2 model, which uses that rather different multi-head latent attention mechanism? That seems like a crucial test of the method's generalizability.
Absolutely. The successful application to DeepSeek Coder v2 highlights the versatility of XKV. On the RepoBench-P and LCC coding benchmarks, XKV achieved around 3x compression without any noticeable degradation in performance.
Wow, no loss in coding ability.
Nope. What's particularly noteworthy is that both Minicache and single SVD struggled to preserve accuracy on this MLA-based architecture, even at considerably lower compression rates. This suggests that XKV's core principle of leveraging the alignment of dominant singular vectors is more robust and adaptable to different underlying attention mechanisms than methods that rely on token-level similarity or purely independent per-layer compression.
The paper also details some interesting ablation studies, specifically looking at the effects of compressing the key and value caches separately. What insights did these experiments provide?
Yeah, the ablation experiments conducted on the ruler benchmark yielded some valuable insights. They found that applying XKV to compress the key and value caches independently consistently led to accuracy improvements across a range of compression rates. Interestingly, the results suggested that the key cache tended to be more amenable to compression than the value cache.
Keys compress better.
Seems that way, which aligns with their earlier eigenvalue analysis presented in the paper. Furthermore, the ablation studies indicated that the optimal compression ratio was not uniform across different tasks within the benchmark, implying a degree of task-specific sensitivity to compression.
So one size doesn't fit all tasks.
Exactly. For example, question-answering tasks appear to tolerate higher levels of compression compared to other types of tasks. This suggests that a static one-size-fits-all compression ratio might not be the most optimal strategy for all scenarios.
That makes perfect sense. Different types of information encoded in the keys and values, and the varying demands of different tasks would naturally lead to different levels of redundancy across the network.
Precisely. The author's in-depth analysis, using both centered kernel alignment to reveal the highly aligned basis across layers and eigenvalue analysis to support the horizontally concatenated KV caches require lower rank observation, provides a strong theoretical and empirical foundation for the effectiveness of the XKV approach. Figure 2 in the paper visually summarizes these key analytical findings.
And of course, there's Figure 3 in the paper, which offers a visual representation of the entire XKV process during both the prefill and decode stages, helping to solidify our understanding of the mechanics.
Yes, Figure 3 provides a clear and helpful visual overview. It illustrates the horizontal concatenation of the KV caches from a selected group of layers, the application of the cross-layer singular value decomposition, and the resulting shared token basis, along with the individual layer-specific reconstruction matrices. It's a great way to see the whole process flow visually.
So while XKV appears to be a significant step forward, the authors also discuss some limitations of their current work and point towards potential avenues for future research and improvement. What are some of the key areas they highlight?
Well, one of the primary limitations they acknowledge is that the current implementation of SKV employs a fixed rank ratio for compressing both the key and value caches across all layers and all tasks.
Right, the static ratio we mentioned.
Exactly. However, their ablation study results strongly suggest that a more fine-grained approach, where the compression rate is dynamically allocated to different layers or groups of layers, and potentially even tailored to specific tasks, could lead to further performance enhancements. Different parts of the network and different types of tasks might indeed have varying sensitivities to the level of compression applied.
That seems like a very promising direction for future work, to have the compression adapt intelligently to the specific demands of the input and the tasks.
Exactly. The authors also emphasize the need for a comprehensive end-to-end system evaluation to fully assess the impact of XKV on actual decoding speed and overall inference throughput in real-world deployments.
Oh, right. The SVD has some cost, and the reconstruction does too.
It does. While they report on the computational overhead of the online SVD during prefill, a complete system evaluation would need to consider the added computation for the reconstruction step during decoding as well. However, they are optimistic about the potential for combining XKV with other orthogonal optimization techniques, such as sparse attention mechanisms.
Ah, like combining memory saving with speed-up techniques.
Precisely, drawing inspiration from works like Shadow KV, which demonstrated throughput improvements with single-layer SVD. Finally, exploring task-specific or even context-aware dynamic allocation of the compression rank remains a key area for future investigation.
So, to bring our deep dive to a close, what are the key takeaways that our audience of AI researchers and ML engineers should remember about the XKV paper?
Okay, firstly, SKV presents a highly effective and relatively straightforward plug-and-play method for significantly compressing the key value caches in long-context large language models by intelligently exploiting the inherent redundancy that exists across the different layers of the network.
Exploiting that cross-layer similarity.
Yes. The core breakthrough lies in the realization that while individual token similarities might be low, the dominant underlying structural patterns of information storage, as captured by the aligned singular vectors, are remarkably consistent across layers.
The shared themes.
The shared themes, exactly. By leveraging cross-layer singular value decomposition, XKV achieves substantially better compression ratios with comparable or even improved accuracy compared to existing state-of-the-art techniques, particularly outperforming previous interlayer compression methods like mini-cache.
Yeah, beats the competition soundly.
It does. Its successful application to architectures employing multi-head latent attention further underscores its versatility and broad applicability. Ultimately, this research offers a very promising pathway towards enabling more efficient deployment and scaling of LLMs with exceptionally long context windows, which is crucial for unlocking their full potential in a wide range of complex applications.
That's a fantastic and concise summary, hitting all the crucial points. Now for our concluding provocative thought. Given the task-dependent nature of optimal key and value compression uncovered in the ablation studies, how might future research develop mechanisms to dynamically adjust the rank? compression parameters based on the specific characteristics of the input prompt or the particular task the model is currently performing. Could this kind of intelligent adaptive compression lead to even more substantial gains in both efficiency and accuracy?
That's a compelling question to consider, yeah. Imagine a future where the model can introspect its input and the task at hand, and then automatically fine-tune its KV cache compression strategy on the fly. This level of adaptability could lead to significant breakthroughs in resource utilization and potentially unlock even better performance for a wider variety of applications. It's a really exciting direction.
Absolutely fascinating. Well, we've really just scratched the surface of this incredibly insightful paper. For those of you in our audience who want to delve into all the technical details and the experimental setup, the link to the full paper and the publicly available code is in the description below. We highly encourage you to check it out.
Definitely worth the read.
We're also keen to hear your thoughts on cross-layer compression techniques and how you envision methods like XKV impacting the future landscape of LLM deployment. Please join the discussion in the comments section below. And as always, thank you for tuning in to AI Paper Podcasts. Let us know in the comments which cutting-edge AI papers you'd like us to unpack for you next time.